Now this looks exponentially harder than before. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are investigating one of the fastest growing basic function, exponential functions. Exponential functions are functions that are formed by this standard form. F of x is equal to a times b to the x plus k. As you can see, exponential functions are functions where the input, x, is in the exponent of the function as opposed to the base of the function, like with power functions, but this time the base of the function is a constant, b. Exponential functions move much more quickly than power functions because the input isn't just multiplied by itself a set number of times, like with power functions, but instead we have a base b that is multiplied by itself the input number of times, which keeps changing. Let's take a look at these two functions. G of x is equal to x squared, and h of x is equal to 2 to the x power. Now, what happens when I plug in different values of x? So, for instance, g of 0 is equal to 0, and h of 0 is equal to 1. Okay, that's pretty close to each other. What about g of 2? G of 2 is equal to 4, and h of 2 is also equal to 4, so they're actually equal at that point. But when we get beyond 2, what happens? So h of 3 is equal to 8, and g of 3 is equal to 9. And look here again, at x is equal to 4, we get g of 4 is equal to 16, and h of 4 is also equal to 16. So they're equal again, but after that, check this out. G of 10 is equal to 100, but h of 10 is equal to 2 to the 10th power, which is 1024. So we haven't even gotten to big numbers for x yet, and we still have a 10 times difference between the exponential function and the power function. Now, if we go to even larger values of x, we get something like x is equal to 100, g of x is equal to a respectable 10,000, but h of 100 is equal to this, which is over 1 nonillion. Properties of exponents deserve their own video, but for now we're gonna just talk about the basics of what exponentiation is. So if I take a number, say b, our constant base here, and I raise it to the 2 power, that means that I'm multiplying b twice by itself, so b times b. If I take b to the 10th power, I multiply it by itself 10 times, so b times 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 b. b is our base, which again is a constant value, and also must be positive, because otherwise then we'd get weird, undefined functions if b were negative. If b is greater than 1, then it is increasing along its entire domain, which is known as exponential growth. If b is between 0 and 1, then the function is exponential decay, and it decreases along its entire domain. Now, if b is equal to 1, then we get the trivial case of the function y is equal to 1, which is just a horizontal line, which is not terribly interesting. A is our leading coefficient, just like it always is. And if k is equal to 0, then a is sometimes known as our initial value of the function. It's called this because of what happens when x is equal to 0. When x is equal to 0, the exponent is equal to 0, b to the 0 power, anything to the 0 power except 0, is equal to 1. So a times 1 is just a, so f of 0 for any exponential function is going to be equal to a. Again, assuming that k is equal to 0. Now, if k is not equal to 0, then the initial value of the function is just 0, a plus k. K represents our vertical shift of the function, and it also represents the horizontal asymptote of the function. So for our basic exponential function, so a times b to the x power, again where k is equal to 0, we have a horizontal asymptote at y is equal to 0. But say this is a times b to the x power plus 1, then my horizontal asymptote jumps up to y is equal to 1. If k is negative, say negative 3, I get a horizontal asymptote at y is equal to negative 3. The domain of exponential functions is all real numbers, negative infinity to positive infinity. The range of the function is determined by both k and a. So for instance, if a is positive, the range of the function will be from k, non-inclusive, to positive infinity. And if a is negative, then the range of the function will just be from negative infinity to k, non-inclusive. End behavior is determined by both a and b, and this is because a determines our vertical reflection of the function, much like we've seen in other function families. And b determines whether the function is going to be exponentially growing or exponentially decaying. The end behavior can be summarized in a table like this, dependent on values of a and b. No need to memorize this table, but we can see a few patterns arise from this table. So for instance, we can see that there are two end behaviors that are exponentially growing, and we have two end behaviors that are exponentially decaying. We also have two end behaviors that are concave down, and we have two end behaviors that are concave up. And these concavity patterns don't coincide exactly with one exponential growth or exponential decay or the other. There's actually one concave up for exponential growth and one concave down for exponential growth, and there is one concave down for exponential decay and one concave up for exponential decay. Not all exponential functions have zeros. In fact, our basic exponential function, y is equal to a times b to the x power, has a horizontal asymptote and does not have any zeros. But if k is negative, so the function is shifted down, I can have a zero for these functions. This zero is equivalent to the log base b of negative k over a. Finally, transformations. We've already seen that k can vertically shift the function up and down, but as usual, our leading coefficient a also stretches and squishes the function, as well as reflects the vertical reflection of the function if it is negative. b also tends to stretch or squish this function, but more dramatically than a does. Now, couldn't I write this function like this? A times b to the dx plus h power, and then plus k. What about h and d? Well, we'll talk about general formulations of transformations in a later video, but for now, for exponential functions, we can see that d and h are actually redundant properties that can be expressed by either a, b, or a combination of the other constants in the standard form of these functions. So for instance, let's take h. Because b to the dx plus h power can be rewritten as b to the dx power times b to the h power, I can say that b to the h power, that's just a number, and a is just a number, so I can combine a times b to the h power into a single coefficient, which I'll call a. So adding a term in the exponent h is the same thing as manipulating a. Similarly with d. So let's set h equal to 0. And if I have b to the dx power, that is the same thing as saying b to the d power to the x power by properties of exponents. But b to the d power is just another number, so I can call that number b. So d just does the same thing that changing b would do. A side note here, a reflection across the y-axis is often represented by multiplying x by -1. But if we do that here, that's the same thing as writing this as b to the -1 power to the x power. But b to the -1 power is just the reciprocal of b. So if b is greater than 1, now 1 over b is between 0 and 1. But if our base is between 0 and 1, that means we have exponential decay. So exponential decay is analogous to a horizontal reflection across the y-axis of exponential growth. Next time we'll tackle a problem involving exponential functions, but in the meantime, why don't you try it out yourself? What is the value of f of 4 if f of x passes through 0, 5, -3, 1027, and 1, 13 over 4? Try it out yourself, and I'll see ya in the solution.